Hi, I'm Dr. Jerry Tanney, your host and guide for the film you are about to see on the story of desalination of seawater in Israel. Now, every good film needs a hero who is shaped by and succeeds in overcoming challenges. The story could be about a prime minister who has the right instincts to recognize drought as a major threat and that desalination plants are the answer, but he has to fight tooth and nail against a Treasury Department that doesn't want them. Why were they dead set against desalination plants? Because it meant long-term contracts to buy water from the plants, even though other people will bear the cost of building and running them. That meant spending money on water that could fall from the sky for free.
In 10 years, Israel has built 5 desalination plants along its Mediterranean coast. In Ashkelon, Ashdod, Sorek, Palmachim and Hadera. Each cost around $400 million. They're privately owned and sell their water to the government, which sells it on to the people. 10 miles south of Tel Aviv, the Sorek plant, open only 18 months, calls itself the world's biggest seawater desalination plant of its kind. It can produce more than 600,000 cubic meters of drinking water a day, enough for 1.5 million people, almost a fifth of Israel's population. Avshalom Felber is CEO of IDE Technologies, which built the Sorek desalination plant.
This is where the water from the Mediterranean enters the plant.
Exactly. Under here, there's a deep pit going about 70 meters down, where all this water is collected and it comes by gravity from the sea, just under sea level. The pumps here lift it from here, from this pit, to the pre-treatment area.
From pre-treatment, the water moves through a series of smaller and smaller screens and filters. Then the water's piped into this complex of buildings, where a fine membrane is used to remove the last bits of salt and other minerals.
There's about 2,000 pressure vessels here that shoot water down through the membranes at a pressure of 70 atmospheres. Halfway down, the water becomes drinking water.
The desalinated water finally passes through these pipes to enter Israel's water grid. This tap is always open to check at every instant the quality of the water that Israelis will drink.
45 minutes ago, this was seawater, and now drink it and see how tasty it is.
Fortunately for us, the prime minister prevailed, and 75% of household water in Israel is today provided by those plants. Could be a great film, but this is an election season, and I don't want to be accused of political interference. So in this film, the hero isn't a person, but a technology called reverse osmosis, with a supporting cast of some of the scientists and engineers who shepherded it to success. I had the good fortune to personally know that group and learn the challenges they faced. My goal is to give you the inside story of the science and the engineering solutions. So let's go back to the start of things before our hero was born. In 1956, Israel's great prime minister, David Ben-Gurion, foresaw the wide use of desalting seawater. For him, irrigating the desert with purified seawater was no delusion but a challenge that could change the primal order by force of the power of vision, science, and pioneering capability. In 1961, his government founded a company called Israel Desalination Engineering, today known as IDE Technologies. Their goal was to provide fresh water for Eilat, then a small town on the Red Sea. Alexander Zarkhin, a Russian Ole engineer, proposed to desalt seawater by freezing it. Now, creating pure water from seawater is complicated. Apart from the high salt concentration, it also contains calcium and magnesium, and both living and inorganic particulate matter. The advantage of Zarkhin's idea was simplicity. When you freeze seawater, ice crystals of pure water are created, together with a very concentrated brine, which drains off. One key problem is the thin layer of brine that clings to the ice crystals and must be washed off to produce potable water. By 1964, the process was scaled up and supplying drinking water to Eilat. However, the cost of the water was simply too high, and the plant's operation was stopped in 1967. Well, if you can't freeze water at a competitive price, maybe you can evaporate it. IDE replaces Arkin's process with an imported, cheaper evaporation process called multi-effect distillation, which involves evaporating part of the water under a partial vacuum in several stages. This is cheaper than freezing, but still very expensive water compared to conventional sources. IDE developed its own process, or a version anyhow, called vapor compression. It involves heating the incoming seawater and spraying it onto tubes in a partial vacuum to evaporate some of it. The water vapor is drawn into a compressor, which compresses it into the tubes, which are cooled by the incoming seawater spray, so the water condenses. Thermal systems are energy intensive and therefore costly. IDE's small-scale systems are useful for local water supplies in places that have limited rainfall, where the need for potable water is more important than its cost. IDE produced many of these units for sale around the world. Remember that name, IDE, because we'll return to them later. It's now time to learn about the birth of our hero, reverse osmosis. The idea of producing pure water by reverse osmosis had been suggested as early as the mid-1950s. Certain materials can act as semi-permeable barriers or membranes, allowing molecules of water to pass through them, but holding back salt. If such a film separates water from a salt solution, water will flow from the water compartment into the salt solution. This process is called osmosis. If we apply enough pressure to the salt side, we can reverse the process, hence the name reverse osmosis. Thin, clear plastic films of cellulose acetate were known to be very selective in osmotic experiments, like the one we just saw in animation. The molecular-sized pores allowed water to flow into the salt solution while keeping back the salt in the concentrated side. Theoretically, this was the most energetically efficient way to desalt water. Unfortunately, even under a pressure of 70 atmospheres, the water flow through such films was exceedingly small. Calculations showed that to have useful water flow, the cellulose acetate barrier film could only be 1,000th of a millimeter thick. How could you manufacture and work with something that you can barely see? Enter Dr. Sidney Loeb, the father of modern reverse osmosis, who in 1965 patented the way to make the first practical desalination membrane. We're going to go into the lab to see what he and his partner Suri Rajan actually did. First, they dissolved cellulose acetate in a combination of water-soluble organic solvents. That's the clear, viscous liquid you see in the flask. Then they spread the solution as a thin liquid film about 1/10 of a millimeter thick on a support and immersed it in a bath of water, just as you see here. The water bath causes the cellulose acetate to come out of solution as a white microporous film. Pictures of the cross-sections of films made this way can be taken using a powerful microscope. They show different spongy porous structures that depend, for example, on the solvents that you chose, or on how much cellulose acetate you put in solution, and even on the temperature of the water bath. The large pores in the sponge can filter particles like bacteria, but can't separate salt from water. However, with just the right combination of solvents and cellulose acetate, Loeb and Suri Rajan found that you can produce this structure, in which the top side is a dense film of cellulose acetate with molecular-sized pores, which is mechanically supported on a microporous structure. Because the dense film is only 1,000th of a millimeter thick, as predicted, it has the combination of flow rate and salt retention necessary to make reverse osmosis a practical process. Now, there were two groups of workers trying to move our hero forward: the engineers, who worked mostly in private companies, and the academics. Initially, I joined the academics with Professor Ora Kedem at the Weizmann Institute. Now, in 1970, a large group of students and senior investigators were already devoted to the study of membrane separation processes. Much of my own work involved understanding the connection between the physical nature of that viscous solution and the complex structure that formed when it was placed in water. So I never really got involved in actually making real reverse osmosis membranes. Professor Kedem worked on understanding the connection between the water and salt flows through the membrane, the molecular pore size, and the charge and salt size of the salt ions. Now, one of her many important theoretical contributions predicted that relatively large ions like calcium and magnesium that also carry a double positive charge will be separated very effectively by slightly larger diameter pores that have much higher water flow rates, but only hold back a low percentage of sodium salts. Now, this turns out had practical consequences. In the Negev desert, there are water sources called brackish water, which have a high concentration of calcium and magnesium that make them impossible to drink or use for irrigation, but could be treated by reverse osmosis. In addition, by adjusting the formation conditions, we could manipulate the pore size in the cellulose acetate reverse osmosis membranes. Just as Ora had predicted, in the lab, we could show that the calcium and magnesium ions were largely retained, and the water flow could be significantly increased at low pressure with large pore size membranes. It was the engineers who figured out how to translate these discoveries into useful systems that were installed in settlements in the Negev. Dr. Mark Wilf is one of Israel's pioneers in reverse osmosis, a former VP of RO membrane development at Hydronautics Corporation in the United States, and currently a consultant and lecturer on reverse osmosis technology.
My work in desalination started in Mekorot in 1977. That time in Israel, the desalination method was the Zarhin, or Israeli desalination technology of today, a process which was developed by Israeli desalination technology, was very effective as far as the materials of construction and the process, but had this natural limitation of evaporation method, which required a lot of energy. And Mekorot started to look for something which will consume less energy, and reverse osmosis was natural candidate. And they built the first brackish water system. Maybe it wasn't the first, but first one which was commercial was in Eilat, Tzapcha plant, which in steps grew up, but mainly it was the brackish water desalination.
However, cellulose acetate also had problems, as Dr. Wilf explains.
Cellulose acetate, the salt rejection wasn't that great, and stability was easier.
So while Leb had found the way forward, reverse osmosis membrane developments still had a long way to go. For the next couple of decades, scientists searched for other plastic materials and solvent combinations to improve upon the cellulose acetate membrane. For the most part, it was unsuccessful. Materials either didn't let enough water into the pores, or they let too much salt in as well. And even when they had the right water flow and salt retention, most were exceedingly difficult to dissolve in organic solvents and prepare with the correct film structure of the lab Surirajan membrane. However, in the mid-1970s, Dr. John Cadott found a way around these problems and succeeded in creating a membrane with salt rejection and flow properties significantly better than cellulose acetate. His approach was to build what's called a thin film composite. He started with a microporous membrane on a support and then used a chemical reaction on the top surface of this membrane to form a very thin layer of selective membrane. The following short film from the Hydronautics Corporation explains how it's done.
We begin the process with a fabric support base and then coat it with a microporous polysulfone layer. This provides additional support for the top 0.2 micron thick membrane barrier layer. This top barrier layer makes the actual separation to purify the water. The semi-permeable polyamide layer consists of a thin film of polymeric material a few thousand angstroms thick, formed on a porous supporting material. Hydronautics manufacturing procedure enables independent optimization of the distinct properties of the membrane support and salt-rejecting skin.
The new synthetic membrane layer not only stopped 99.8% of the salt, but also had greater water flow and long-term chemical stability than cellulose acetate. It remains the best reverse osmosis membrane used today. Making small sheets of membrane for laboratory tests is fine for academia, but making a reverse osmosis technology commercially available requires reliable production of millions of square meters of membrane per year. Once again, it was the engineers and private companies that provided the way forward. Let's visit a typical reverse osmosis membrane manufacturing facility and see it done in action. Typically, a membrane batch today contains 10,000 square meters. The casting solution is continuously applied to support fabric. The coated fabric then enters a large water bath where it runs up and down over rolls to increase the time spent in the bath. Excess water is squeezed out of the membrane, and the membrane runs through an oven to dry, after which it is rolled up. Producing a good reverse osmosis membrane is the first step, but engineers now had to find a design to package that membrane into equipment for working reverse osmosis systems. The design needed to meet three fundamental requirements. Number one, it had to pack a lot of membrane surface into as small a volume as possible to minimize the total size of the system. Number two, it had to be reliably and inexpensively manufactured to withstand up to 70 atmospheres of water pressure. And number three, it needed to generate turbulent flow over the surface of the membrane. Now, the first two requirements are easily understood, but the last is not so obvious. Why do we need turbulent flow over the membrane surface as well as high pressure? In one word, the answer is mixing. Retained salt and any particulate matter pile up at the membrane surface when the water flows through under pressure. If too much salt accumulates near the membrane surface, its osmotic pressure will literally pull the water back. To keep the membrane water flow rate and salt retention at their highest values, we need to quickly move away the concentrated salt water near the membrane and bring in new solution to be desalted. The answer was the spiral wound module device, which has become the most popular engineering solution for packaging membrane. The following short film from Hydronautics Corporation shows how this is done.
The membrane flat sheet is then combined with a sheet of feed channel spacer. This provides turbulence and creates space between the membrane sheets to allow uniform flow of the water to the entire membrane surface. The leaves of membrane and feed channel spacer are then combined with a sheet of permeate spacer, which provides open flow channels for the permeate even under high pressure. The leaves are glued along each of the 3 exposed sides and then rolled around the core tube. With the back of the membrane completely sealed to the edges of the permeate spacer, the feed water is forced through the feed channel spacer, contacting the front or barrier layer of the membrane. Clean water, or permeate, passes through the membrane surface into the permeate channel and then flows in a spiral direction to the center of the element and is collected into the core tube. Hydronautic spiral wound elements can then be loaded into pressure vessels and interconnected with additional elements to complete any number of design specifications. Once the end adapter is connected to the last element and the pressure vessel is sealed, feed water can be introduced and then treated. The feed water that does not permeate through the membrane becomes enriched in salts as it travels through the feed channel spacer due to permeate water being removed. Typically, 8 to 10% of the water is removed in one 40-inch long membrane element. The permeate water then flows out the end of the vessel and is collected as the product. And the reject or concentrate from that vessel may then flow through another vessel producing.
So, let's go through that again because it's a bit tricky. We make an envelope of 2 sheets of membrane by gluing them together on 3 sides, in which the thin selective membrane is on the outside surface. Inside the envelope is a plastic spacer that prevents collapse of the envelope under pressure and allows the pure water that comes through the membrane, through the 2 membranes, to flow along into the central drain tube, which is attached to the 4th side of the envelope. Now, between the envelopes, we have a second plastic spacer. This spacer allows the water to flow across the membrane surface and is designed to create turbulent flow in the channel to get good mixing and prevent salt from concentrating near the thin membrane. By winding the envelopes around the central core tube and putting the whole assembly into a plastic housing, we get a spiral wound module. Now, even having gotten this far, reverse osmosis could have been confined to small, expensive systems in niche applications were it not for the investment made in module manufacture. Initially, the spiral wound elements were built by hand. Defects in the membrane and the gluing operations led to scrap rates of 20 to 30% of the final modules. Automation drastically improved production, efficiency, and reliability, and decreased production and final system costs. I promised you the inside story, so let's visit a semi-automated manufacturing plant and watch spiral wound reverse osmosis modules in production.
And there is a rolling automatically and closing, and then come to the testing. Some of the companies, you just come, there's almost the only people who are there on the floor, people who do the maintenance. Everything else is done by the huge, relatively big robotic installation.
Now let's summarize the progress our hero has made so far. Reliable, high-volume manufacturing of a membrane element with 99% salt retention and good water flow. A compact, efficient module design for engineering large systems. Reliable, efficient, low-cost manufacturing systems to build those modules. However, reliable manufacture of membrane modules was still not enough to make our hero competitive in large water installations. The question was, what happened to their performance on real water sources over time? The operation of the reverse osmosis system was smooth enough if it was desalting a pure salt solution. But seawater has lots of particulate matter as well. Some of the inorganic particles are extremely tiny and difficult to remove by pretreatment. These particles reduce membrane performance by sticking to and building up on the membrane surface and prevent the turbulent flow from removing salt retained by the membrane. In addition, the biological particulates can grow inside the membrane elements in a phenomenon called biofouling. This also causes loss of membrane performance. Now, a system supplying cities with drinking water must reliably supply all the water needed all the time and can't afford to be changing membranes every few years. It also needs to work perfectly with minimal staff. IDE got into the business of building reverse osmosis plants and became very expert at building and running them. Dr. Boris Lieberman, the director of RO Research and Development at IDE Technologies, and one of Israel's true experts, explains how the breakthrough began with understanding the living nature of seawater and how to pre-treat the water before reverse osmosis.
We made a significant way to understanding the seawater. And this was mainly the most important step. Because people look on the seawater in the past like water with salt, and this is not. It is water with living organisms, huge amount of bacteria, algae, fish eggs, and those living organisms are the most important challenge in desalination. So instead of, first step was the killing those organisms, put a chlorination, kill them, and try to remove them. And this approach was long time, maybe 10, 15 years in the business, then people try to kill it. But when you kill those organisms, you get the organic material from them. You get the nutrients, you convert it from living organisms to nutrients. What is the food for bacteria? And you are coming to the biofouling problem. It was to understand that we don't need to kill nothing. We have to separate it as gently as possible. And separate it gently means make filtration by a small differential pressure, so not to destroy the algae.
This is what the pre-treatment system looks like in practice at the IDE Ashkelon installation.
3 huge pipes channel raw seawater into a pumping station located on shore. The pumping station then channels the water to a series of intake pools. From the intake pools, the water undergoes 2 filtrations. First, it seeps through layers of anthracite and special sands. Then it's pumped through micronic filters. Now the water is ready to begin desalination.
The last piece of the puzzle needed to make the cost of desalting seawater by reverse osmosis more competitive than thermal processes was the invention of energy recovery systems. The energy needed to create high pressure was only a small fraction of the pumping energy needed to create turbulent flow over the membrane surface. In the early systems, this energy was effectively lost. However, very clever engineering came to the rescue, as this animated explanation shows.
As the pressurized seawater enters the pressure vessel and flows across the membrane surface, the water molecules are forced into and through the membrane envelopes, leaving the salt molecules behind. The desalted water passes through the membrane and emerges at low pressure, where it is collected in a tube and directed to one end of the pressure vessel. The concentrated salt stream that is rejected from flowing through the membrane continues to pass across the membrane surface, where it is collected separately. The concentrated salt stream retains about 55% of the total energy of the seawater stream that was originally fed to the membranes. To reduce the energy that is required to operate the reverse osmosis plant, the pressurized concentrated stream is piped into an energy recovery device. Here, up to 98% of the energy of the concentrated salt stream is transferred to an equal volume of the incoming seawater in an isobaric energy recovery device. The energy recovery device significantly reduces the plant's operating costs by recovering the concentrated salt stream energy and using it to pressurize 60% of the seawater that is fed to the membranes.
We can see what energy recovery systems look like in real life at the Ashkelon reverse osmosis plant, one of the 3 plants IDE has built in Israel.
Waste brine is directed to an energy recovery system. Here, huge pistons transfer pressure to half of new seawater on its way to the reverse osmosis membranes. With no need for energy-consuming high-pressure pumps, this saves over 50% of the energy required.
It was an additional step in the post-treatment to bring back the calcium that you removed during desalination and bring the bicarbonate that people need. Similar what it is in the nature, when the rain is going and collect the CO2 from the atmosphere, cleaning the atmosphere from the CO2 gas coming to the marble in the mountains, dissolving them, bringing to the groundwater the calcium and the bicarbonate. So we are studied this process and make exactly the same.
With 75% of household water being supplied by reverse osmosis, Israel has become a world leader in water reuse and low-cost seawater desalination.
And also the cost of the water was diminished dramatically. If the cost was something about $9, $10, $7, $8, the last tender in Sorek 2 was 1 shekel 45 agorot.
Leadership in treating sewage has taken place over the last 15 years. The breakthrough has been in the development of membrane technology for desalination, because that breakthrough in technology dramatically reduced the cost of desalinating seawater.
From about $1 a cubic meter to about 40 cents.
Exactly, to less than half the cost.
Since its founding in 1961, IDE has gone on to build seawater desalination plants using both thermal and the reverse osmosis systems in countries around the world. And what of Ben-Gurion's vision to use desalting to water the desert? It too has come to pass, even if it isn't quite the way he might have imagined.
It's a perfect little recycling ecosystem. The waste from the people of Rahat over there is treated here and then used to irrigate the fields nearby.
Dr. Lieberman left us with a vision of IDE's current development project, which is truly breathtaking. It involves another invention of Dr. Loeb in which the flow of water caused by the osmotic pressure of a very concentrated salt solution can be used to drive a turbine and create electrical energy. In hydraulic terms, a 33% salt solution has the driving force of Niagara Falls.
Where we take water from the sea, make desalination, invest about 3.3 kilowatt hour to make this desalination, send it to the Tiberias. This part of the project is already in construction. So the water we will not take anymore from Tiberias. We will put water in Tiberias back. It can be million cubic meter a day. And this amount of the water will go through the Jordan River and recover this Jordan River. And when it will come to the Dead Sea, on the contact point between saline water of Dead Sea and fresh water, what we make desalination, and when we make the contact with Dead Sea, but it is 33% salinity, we recover 3 times more energy. Of making desalination, transportation, and bringing it to the Dead Sea will be paid by energy developed during this process.
The Bible promised us, "Ushaftem mayim b'sason mimaynei hayeshuah." You shall drop water in gladness from the springs of deliverance. When those words were spoken, how could we know that we would one day build those springs on our seashore?